Welcome to another podcast. In this episode, we're going to be taking a look at the ideas behind what is called the resonant frequency for a damped harmonic oscillator, and this involves the gain. Now, let me just remind you from the previous video that when we looked at the gain was defined as being 1 over the quantity square root of we had omega naught squared minus omega squared squared plus ends up being 2p omega quantity squared. Now remember, all of this was looking at the damped harmonic oscillator given by this equation where we have a natural frequency of omega naught and we have a driving frequency of omega. And so this is the situation that we are still in for this video. We're going to look at equations of this type. And we figured out that the gain was the determining factor in the amplitude. And I have sort of a follow-up question here, and the question is, for what value or values of omega is the gain maximized? What this is going to tell us is I'm looking for some omega, which I'm going to call omega sub res, that's the resonant frequency, such that when I have my solution x sub p, so remember x sub p is a cosine, so let me back up a second. It's a times the gain times the cosine of omega t minus phi. I'm looking for the value of omega such that when I plug that value in, so g at the resonant frequency times cosine of the resonant frequency, what we end up getting is we end up getting a maximal response, which means that we end up with a maximal maximal amplitude. Now, we saw that in the absence of damping, the maximal amplitude tends to infinity as time goes to infinity. But in the case of damping, damping exists so that that won't happen. But just because there's damping does not mean that we will not get a spike in the motion when we get close to the frequency that would cause resonance. And what you learn is in the videos that we had before where there was no damping, if the driving frequency was omega, then omega is the resonant frequency. In other words, omega naught is the resonant frequency. So if omega were equal to omega naught, then in the absence of damping, the resonant frequency is the natural frequency. However, what I'm interested in is if I do have damping, what does the resonant frequency become? Now, we're talking about maximizing a function of the variable omega, which means I'm going to take the derivative of that function with respect to omega and set it equal to 0. Now, I know you're thinking, oh goodness, I hope he doesn't do this by hand, and don't worry, I'm not. Trying to take the derivative of that with respect to omega by hand is just not worth our time. So what I'm going to do is bring in Maple now, and Maple's going to do it for us. So you can see here that I have the gain defined. Let's go ahead and enter that as a function. And I'm going to go ahead and differentiate that with respect to omega just to show it to you. So there's the derivative of that. And then I'm going to solve that, and actually I think I need to restart this because I had it in a previous thing. So let me quickly restart this. I've got one of my variables assigned here. There we go. That's better. That's better. All right, we ended up with 3 possible frequencies that would provide a maximal response. One of those is if the frequency is equal to 0. But if the frequency is equal to 0, then we're not actually driving it with anything. We don't get any sort of oscillation to occur, so that one doesn't make any sense. And we end up with a pair of roots that are plus or minus each other. Of course, these are going to be complex conjugate roots, otherwise we would not have oscillations occurring. But the negative root here makes no sense because we're talking about a frequency, so the negative frequency doesn't really compute for this case. So what I'm looking at there is the value omega naught squared minus 2p squared. So let me quickly jettison this and then we'll come right back to it. What we just calculated in that exchange was that the maximal resonance frequency is given by this square root of omega naught squared minus 2p squared. And I want to talk about this for a second because this is where students make some mistakes. So this is the big thing coming out of this. I want you to focus on the fact that it's not 2p quantity squared. What a lot of students will do wrong is they'll just take this value and they'll square it, and that's not what this says. It should be 2 times take the p value and square it separately. And so this turns out to be the resonant frequency, and what I want you to notice is when p is equal to 0, meaning there's no damping, then the resonant frequency is the square root of omega naught squared, which is omega naught, which matches what we predicted before because we've looked at this in the case where there wasn't any damping. So this turns out to be the resonant frequency. Let's bring Maple back in. We're going to do an example with this now. On your Maple lab, you have a couple of problems where you're going to look at plotting the gain versus the frequency. So I wanted to take a look at that with you. So I have a differential equation here. And what we've defined is for this particular differential equation, the natural frequency is 5. It's the square root of that term. So let me go ahead and enter that. And then the p-value for this problem, remember this is 2 times p. So the p-value is that value divided by 2. Go ahead and enter that. And then I'm going to use the gain function that I had up above. I'm going to enter that. So this is what the gain looks like for this particular problem. And now I'm going to plot that for gain values between, or for frequency values between 0 and 10. Remembering that the resonant frequency is going to be somewhere near 5. So that allowed me to come up with a nice interval here from 0 to 10, putting 5 in the middle that made sense. And so here's the plot. What you can see is that the amplitudes of the oscillation remain relatively low. So if the A value for the problem was 1, we would get amplitudes less than 0.2 for the majority of frequencies, but as we approach near 5, we're going to get a spike in amplitude up to 2. And depending on what you're looking at, 2 may be a big enough value that you might want to invest in more damping. Taking this one step further, if I calculated the resonant frequency, remember that's the square root of omega naught squared minus 2p squared, calculating that for this problem, you can see that a frequency not exactly 5, but near 5 is going to give me resonance. Now the reason it's so close to 5 is if I go back up and look at the damping, there's very little damping here. My damping constant is 0.1 divided by 2, or 0.05. So there's very little damping occurring. Let's up that considerably. Let's replace it with the damping constant of, let's say 1. And if I do that, then the only thing I need to change is my p-value here. Then recalculate the gain, replot it, and notice there's not as pronounced a spike. The oscillations themselves are smaller. If you remember the previous, it was 0.2 was the amplitude of the oscillation for most of the time, and then it got up to a spike of 2 near 5. But here it's only spiking at about 0.2. And the resonant frequency is actually a little bit closer, or a little bit further away from 5, closer to 4 at 4.94. The more I up the damping here, let's say a damping of 5, then the more likely we are to damp out the motion completely. And you see here there's just a little bit of a spike. That spike is occurring closer and closer to 4. And if I calculate the resonant frequency here, the resonant frequency turns out to be at 3.5, which makes sense, right around there. And eventually what's going to happen is we're going to push this damping constant up so high relative to this that we don't get damping at all. That we don't get oscillations at all. And when that happens, it turns into the underdamped case. This 5 is kind of the breakover point for that. And so let me put 10 in instead. And you'll see that if I up the damping to 10, then the resulting plot has no spikes at all and it goes directly back to equilibrium. This is now the overdamped case. And so you can see the relationship here between changing the damping value and then the resulting amplitude response, and then once you have the resulting amplitude response, looking at whether or not you get a spike in the resulting motion. So I'll go back to one that spikes a little bit more, damping coefficient of 0.2. And so you can see this nice spike with an amplitude of 1 in this case that occurs near 5. In fact, it's 4.997. So this is plotting the gain versus the frequency, and it's an incredibly important tool for analyzing for a given harmonic oscillator where and when you might run into problems, and then designing the system so that there's enough damping to have the amplitude spike that occurs be within a certain tolerance that you're wanting. All right, thank you for watching.